Assalamu alaikum everyone. Welcome to the 17th lecture, the penultimate lecture of this course, I think, for numerical methods course, and the topic is numerical differentiation. Okay, and the plan for today is to understand how we can approximate derivatives. Okay, so far we have discussed at length about what derivatives are, the concept of derivatives itself, and we have also from our previous courses we have also seen how to we have also learned how to calculate derivatives analytically, right? But in our numerical methods course we of course don't do things analytically, we approximate them, right? So today we will learn how to approximate derivatives, and what will we use in order to approximate, in order to come up with the derivative approximations. We'll use some functional values that we are given initially, and those are the functional values at discrete points. Okay, and since we are approximating our derivatives, we are going to incur some errors, right? So we are going to analyze the complexity of the errors that we encounter. And lastly, the third topic is basically discussing about partial derivatives. Okay, and for partial derivatives we are going to use multivariate, or more precisely bivariate functions. And since the function is bivariate, the points that we are going to be given will be grid points. Okay, they are going to be arranged in a matrix, and we are going to use those grid points in order to calculate the partial derivatives of uh, bivariate functions. Okay, so not calculate, we are going to approximate partial derivatives. Okay, so let's begin. So how do we approximate derivatives? Okay, so let's head over to our bamboo paper and discuss it in detail. Okay. So before going to our demonstration, let's discuss about the basic approaches. Okay, so there are three main approaches to approximate derivatives at particular points. So the first one is forward difference, second one is backward difference, and the third one is central difference. Okay, central difference is basically the average of the first two preceding approaches. Okay, so let's go to the pen paper and see how they work. Okay. Okay, so suppose you're given a set of data points, say x1 up to xn. So let's try to plot them in a graph. Okay, so let me draw the axis. So it should look something like this, right? So our x points are along this x-axis, and our y points will be along the y-axis, or this will be my functional values, right? So let's say my data points are distributed in the following manner. So it's something like this, right? So each of these are my data points. So let us focus on three particular data points, okay, in order to discuss the main approaches that we're going to talk about. So let's say this point right here, let me change the color a bit. So let's say this point right here, let's call it our ith point. Okay, so ith data point, right? So let's denote it using, say, the coordinate x sub I comma y sub I, right? So x is my value of my independent variable, and y is my functional value, right? And the value that is after the ith point, this is of course the what? This is of course the I plus 1th point, right? This point over here, this is the I plus 1th point, right? And we are going to denote it using, let me write it a bit more clearly, I plus 1th point, and this will of course be the coordinate x sub I plus 1 and y sub I plus 1, right? Fine. And the value that's preceding my ith point, let's use this color over here. So let's call it this point over here. This is of course my I minus 1th point, right? Because this is the point before the ith point. And this will of course be denoted using the coordinate x sub I minus 1 comma y sub I minus 1, right? This will be my coordinate. Okay, so why did I basically cherry pick these 3 points? Because we are going to use these 3 points in order to calculate the derivative at the point, at the ith point, okay, or at the point x sub I comma y sub I, at this point over here. our goal is to calculate the derivative of the function. So we don't know what the actual function is, right? We only know the functional values at some given discrete points, right? And we're going to use those discrete points or data points in order to calculate the derivative of the function, the unknown function at a particular point x sub I, comma y sub I. This blue colored point over here, okay? So let's see how we can do that. So the first approach is, of course, as I've said before, the forward difference. Okay, so the forward difference, the formula for the forward difference is uh, the f prime. So the first derivative of the function at the point x sub I is approximately equal to y plus y sub I plus 1 y sub I plus 1, which means the point that is ahead of the point at which I am uh, trying to calculate the derivative, the ordinate of that point minus the ordinate of the point at which I'm trying to calculate my derivative divided by the abscissa at those respective, the difference of the abscissa at those respective points. Okay, so which is simply writing x sub I plus 1 minus x sub I, right? So to aid your understanding, let me zoom in on this part of the graph a bit more. So let's say this part of the graph. So let us zoom in on this a bit. So let's say it looks something like whatever I'm going to draw inside this. So our first the point, that's the I minus 1 point. Let's say it's somewhere over here, and let's say our point that's on the middle, the ith point, let's say it's somewhere over here, and the point that's at the front of my ith point, which is the I plus 1th point, let's say it's somewhere over here. Okay, so this is of course my I plus 1th point, this is my ith point, and this is my I minus 1th point. Okay, we're just zooming in a bit in order to help our understanding. Okay, so this forward difference over here, what is it trying to calculate? It's trying to calculate the slope of the straight line that passes through the ith point and the I plus 1th point, right? So essentially it's something like this. So let me try it using a different color, say the red color. Okay, so whatever slope that I'm getting, or whatever first derivative that I'm getting at the point xi, remember that the point xi comma yi is this blue point over here, right? So this straight line passes through, of course this is a very badly drawn straight line, this straight line passes through my blue point and my purple point, right? Which means my ith point and the I plus 1th point. So this slope over here, so our actual curve is something like this, right? Something like this. So we don't know what the actual function is, but we are saying that okay, the value of the derivative at the point x sub I, the first derivative, is the slope of the straight line that passes through the ith point and the I plus 1th point. Okay, so this is what my forward difference says. So this thing over here is my forward difference approximation of the derivative. Okay, now the second one was, if you recall, it was the backward difference, right? So backward difference, let's try to jot down the formula over here. So I'm of course writing it in shortcut, and the backward formula says that the approximation of my first derivative at the point x sub I is equal to the ordinate of my ith point minus the ordinate of my I minus 1 point. Okay, so the I minus 1 point, as you recall, was this green point over here, right? It was the point that was preceding my ith point, right? Okay, so at the numerator we have the difference of the y values, and of course at the denominator we'll have the difference of the abscissa values, right, of the x values. So x sub I minus x sub I minus 1, right? So it says that okay, whatever, so let's denote it using orange right now. Okay, so whatever uh, approximation of the derivative that I want to get at the point I, or at the ith point, we say that that approximation is that first derivative approximation is equal to the slope of the straight line that passes through the I minus 1th point and the ith point. Okay, so this orange or yellow colored straight line that I have drawn through the point, through the green point and the blue point, which are respectively my I minus 1th point and the ith point, the slope of that straight line will be an approximation of my first derivative at the point x sub I comma y sub I, okay, which is the ith point, the blue color point over here. Okay, now as human beings we can see the graph, right? And intuitively we can say, okay, if my data points are showing a pattern which looks something like this, my actual graph should look something like this, right? The function that we don't know, it should roughly look something like this, right? And the value, we can also visualize the slope at the blue point, right? Which should be something like this, right? So this is a bad drawing. So it should be something like this, right? The slope or the first derivative at the blue point should be something like this, right? So let's erase this to drawing, and let's try to see how we can visualize it in our zoomed in version, right? So our actual graph would look something like this. The portion of the graph something like this, let's say, and the first derivative at the blue point or at the ith point, it should look something like this, right? So what can we notice here? The actual first derivative through the point, uh, through the blue point is kind of a tangent at that point, okay? Tangent of the function at that point, right? And you can see that slope is not as big as the red colored slope. That, so of course the colors have been okay. So by red I mean of course this dotted line over here, right? The dotted line that we got for the forward difference case, and the orange line that we're getting for the backward difference case. Okay, these two are our dotted lines, and we can say that our actual derivative or the derivative or the straight line which has a slope equal to our actual derivative lies somewhere in between, right? It's not as high as our forward difference is telling us, and it's not as low as the approximation that backward difference is giving us, right? So our forward difference is giving us this red dotted line over here, and our backward difference is giving us an approximation which is the slope of this yellow or orange dotted line over here, right? And the actual slope, actual tangential slope that we're getting at the point, at the blue point, is somewhere in between, right? So that's where the birth of the central difference formula came, right? So what's the, let me erase the actual function and the derivative. Okay, now let's write down the formula for the central difference. Okay, so the central difference, let's denote it using CD shortcut. So it says that, okay, we are going to take the average of these two slopes. Okay, so we are going to average out the slopes of the orange and the red dotted straight lines. Okay, so it says that, okay, the approximation of the first derivative at the point x sub I is equal to the ordinate value at the I plus 1th point minus the ordinate value at I minus 1th point. Okay, so this time we are taking a span of 2. Okay, so we are taking the difference of the y values of the I plus 1th point. This is purple colored point over here, and the green point, which is the I minus 1th point, right? And again, at the denominator we have the difference of the x values, right? So we are going to write x sub I plus 1 minus x sub I minus 1. Okay. So again, let's introduce another term over here. So let's say, not another term, another notation over here. Let's say whatever discrete points I have, these discrete points, right? Whatever discrete points that have been given, they are equally spaced. Okay, and the step size or the difference between the x values on the x direction is h. Okay, so my step size or the regular intervals at which I'm getting my discrete points, it has an interval of h. Okay, so after each h step, or after each step of h units in size, I'm getting a discrete point, right? So this point and this point are separated by h units, right? Again, this point and this point are separated by h units. Okay, so my writing of h is very bad over here, but I have written h over here. Okay, fine. So this disparity and this disparity are both equal. So forgive my unequal representation. Okay, fine. So what can we rewrite this thing as? Let me switch back to the black color. So this thing can be written as what? Y sub I plus 1 minus y sub I minus 1 divided by 2h. Okay, since I know the distance between x sub I minus 1 and x sub I is h, again I know that the distance between x sub I and x sub I plus 1 is h. I can say that the distance between x sub I minus 1, which is the screen point over here, and x sub I plus 1, which is the x value of this purple colored point over here, is of course 2h, right? So this whole distance is 2h, right? So that's what we are plugging into our formula of our central difference formula over here. Okay, fine. So now that we know how this formula came about, let's try to let's go back to our presentation and see what else we can say about these formulas. So essentially, these three are the formulas that we have just talked about, and of course, the value of h is equal. The value of h is equal to the difference between consecutive x values, right? And I forgot to draw the straight line that we get for the central difference. Okay, so let's go back to our bamboo paper. So of course, our central difference will give us a straight line that's approximately an average straight line slope will be an average of the slopes that we got for our preceding two methods, right? So it should look something like this, right? And as we have seen before, the visual intuition that we get is that the derivative at this point, or the slope at this blue point, or the tangent at this blue point should look something like this, right? And as you can see, the derivative that we are getting as a result of our central difference formula, the approximation that we're getting roughly resembles the actual slope that we are getting at this blue point, right? That's why, as we'll see a bit later in a later segment of this presentation of this lecture, we'll see that why the central difference yields a lesser error than our forward and backward difference formulas. Okay, fine. So visually we can interpret it, right? Because the blue colored dotted line that I have drawn has roughly the same slope as the actual first derivative of the function of the unknown function at the given ith point. Okay, at the given blue colored point, right? So let's try to analyze it more mathematically. Let's go back to our presentation. Okay, so now we are fully aware of these three formulas and we know how they look like when drawn on the graph, right? So let's move on. So let's talk about the errors of our approximation. Okay, since we are approximating, of course, we are going to incur some errors, right? So, so in order to come up with the upper bounds of our errors, we are going to use our Taylor series, okay, or Taylor polynomial more precisely. And if you recall, in our remainder theorem, what did we do? We basically considered a certain number of terms, and for the rest of the terms that we are not considering, we approximated the truncation error, right? So if we are truncating a certain number of terms, we are going to have to come up with a bound of error for those discarded terms, right? And we have seen from our remainder theorem that if we take the first two terms of our Taylor series, the error that we incur for not taking the third term, the fourth term, and so on looks something like this, like h squared by 2 times f, the second derivative of a value c, right? And c falls within our value x and our value x plus h. Okay, so this is of course what we get after invoking the remainder theorem. So this part over here is of course the remainder, and we call the rest of the terms our quotient, right? Or the terms that we are actually considering, we call that our quotient, and the rest of the parts that we're discarding, the approximation of the summation of those parts is called the remainder, right? Okay, so whatever error we are going to incur for the forward and backward difference formulas, it will be on the order h. Okay, so let's see how we get that. So our first job is to somehow take the Taylor series and come up with a formula for the forward and backward difference. Okay, so okay, our goal was to what? Our goal was to get the f prime of x, right? So the left hand side of both of these formulas have f prime of x, right? So okay, so take f prime of x, take it to one side, and whatever else you have remaining, take it to the other side. Okay, so f of x will go to this side over here. So we have, okay, we can also denote f of x plus h as f of x sub I plus 1, right? Because x plus h is of course the point which is h units ahead of my current point x, right? And if we consider my current point as x sub I, the point which is h units ahead of the point x sub I is of course x sub I plus 1, right? X sub I plus 1, right? Because x sub I plus 1 minus x sub I is of course h, and we have seen that we are taking the discrete points at regular intervals, right? Where the interval is h. Fine. So okay, we have f of x plus h minus f of x, which is simply the same as writing f of x sub I plus 1 minus f of x sub I, and we have this h over here, right? So if we take this h from the left to the right, this goes to the denominator, right? So we get divided by h over here for this term, and again for the remaining error term, we have what? We had h squared by 2 times the second derivative at the point c, right? So this h squared divided by the h that we're getting at the denominator will give me h by 2, right? So h by 2 times f double prime of the point C. Okay, and of course C is between x and x plus h. And why did this thing become minus? Because of course we are taking everything to the other side, right? So this plus, if we take it to the other side, this will become minus, right? Fine. So notice that this whole thing over here that we are getting is the same as the formula that we got for the forward difference, right? Simply just replace f of x sub I plus 1 with y sub I plus 1. You get the exact same formula, and just replace f of x sub I with y sub I, and you get the formula for the forward difference, right? And of course our h is of course the difference between the x sub I plus 1 and the x sub I, right? Because our uh, the distance between consecutive x values is of course what? The value h, right? So this thing right here is our forward difference formula essentially. Now, if we just substitute h with minus h, what do we get? We end up with the backward difference formula. Also, just replace h with minus h over here. You should get x minus h, right? And this plus h times f prime x will become minus h times f prime x, right? And this h square by 2 term will remain the same because we know minus h whole square and h whole square is the same thing, right? It's h square, right? Because minus square minus 1 times minus 1 is plus 1, right? Okay, so what changes will we have in the formula? We'll have what? Instead of x plus h, we're getting x minus h. So whatever we'll have uh, at the right hand side of this minus operation over here, it will be what? X f of x sub I minus 1, and whatever we'll get over here will be f of x sub I, right? This thing over here. Essentially, we'll end up with y sub I minus y sub I minus 1, which is the same as writing f of x sub I minus f of x sub I minus 1. And at the bottom, we'll have, at the denominator, we'll have x sub I minus x sub I minus 1, or the distance between consecutive x points, right? Which is equal to x. So the derivation is not that important. Just I did not write it separately. You can simply understand it, right? So this, whatever, if we just plug in minus h in the spot of h, we'll end up with our backward difference formula. Okay. And what are you seeing for these two difference formulas? We're seeing a dangling term which is h by 2 times f double prime of c. Okay, so we can say that the error that we are incurring for approximating our first derivative with these two formulas is what? Is of order h, right? Because this term that we are getting left out with is h by 2, or it has a h factor, right? So whatever errors that we're encountering is of order or ease of complexity big O of h, okay, for both our forward difference and our backward difference. Okay, now let's talk about our central difference formula. Okay, so instead of showing it using my mouse pointer, let's try to flesh it out. Okay, let's go back to our bamboo paper and see how the central difference formula works. Okay, okay, so let's go to next page. Let's go to the next page. Okay, so similarly, just like before, in order to analyze the error of our central difference formula, we are going to invoke the Taylor series. Okay, so if we recall, it was something like this, right? F of x sub I plus 1, we can also write it as something like f of x plus x I plus h, right? Because x sub I plus 1 is essentially the same thing as the point which is h units ahead of x sub I, right? Okay, so using the Taylor series, what do we get? We get the point, the functional value at the point x sub I plus h times the first derivative of the function, so f prime x sub I, so f prime at the point x sub I plus h square by 2 factorial. So this is the simple Taylor series, right? F double prime at the point x sub I plus, so we are going to consider a third degree Taylor polynomial, okay, for the central difference formula. So you're going to have to consider the first four terms, okay. So we have already considered the first three terms, and the fourth term is h cubed by 3 factorial, okay, times f triple prime at the point x sub I. Oh, sorry, not the point x sub I. So since we are capping it off at this term over here, whatever terms we are left out with will give me my error approximation, right? So let's say this is the third order derivative or third derivative at a point c sub 1, okay, where of course c sub 1 is between what, xi and xi plus 1, okay, or more, to put it more bluntly, x sub I plus h. So whatever points we have between x sub I and x sub I plus 1, the point c sub 1 lies somewhere in between, okay, fine. So okay, this is the first Taylor polynomial. So we are going for the central difference formula. We also use what? We also use the functional value at the point x sub I minus 1, right? So let's try to use our Taylor polynomials for this point as well. So it will simply be write it a bit faster. X sub I minus h is equal to our functional value at the point xi. So since we are using minus h on the spot of h, this plus h times f prime x sub I will become what? Minus h times f prime x sub I. So this was the same thing that we saw in the case of our backward difference error approximation, right? So I did not write that down in my bamboo paper just for the sake of saving time. So now you know how it how it happens, right? So when you plug in minus h on the spot of h, this plus h term over here will become minus h, right? And simply put, this h squared term will become what? Minus h whole square, right? So this thing will become minus h whole square, right? So we're not going to write that. We're going to simply write h square by 2 factorial, right? Because that's the same thing. And we have f double prime x sub I. This will of course be I, and the rest of the terms we are approximating it as what? So since the power is odd, h cube, right? So it will of course become minus, right? Minus h cube by 3 factorial times f triple prime at the point, say this time we'll consider the point c2, okay. And of course the condition is what? For the remainder theorem, the condition is that the point c2 will lie somewhere between x sub I minus h and xi, okay, fine. So since we are considering the all the points between x sub I minus 1 and x sub I, so the point c2 is somewhere lie somewhere in between, okay, fine. So these two are our two third degree Taylor polynomials that will be used in order to approximate our error for the central difference formula, okay. So what do we do now? Let's try to subtract these two Taylor polynomials. So what do we get? So let me use a different color, say something like this, the red color over here. Okay, so if we subtract the first Taylor polynomial from the second Taylor polynomial, so this term and this term gets cancelled out, right? So f of the functional value at the point x sub I gets cancelled out. And what do we have? Since the signs are different, it will not get cancelled out. Again, for this term over here, these two terms, the signs are the same, right? So these two terms will also get nullified. And what do we have remaining? We have something like this, right? So we can say that, okay, if x sub I plus 1 minus the functional value at the point x sub I minus 1 is equal to what? Uh, so this minus and this minus will become plus, right? So we have 2h f prime at the point x sub I. Let me draw the bracket a bit more clearly. Okay, x sub I, and this minus and this minus will of course become plus. Then we have what? 2h cube divided by 3 factorial times f triple prime. Oh, sorry, my bad. So these two terms are different, right? So you're not going to sum them up since we have C1 and C2 over here. So let's write them separately. We have h cube by 3 factorial and times the third derivative at the point C1 plus h cube by 3 factorial of the third derivative at the point C2. Okay, so this thing is our difference, that the result of our negation, right? The result of a subtraction, right? So this is what we end up with. Now let's try to use this equation over here and somehow come up with our central difference formula. Okay, so let's rearrange it a bit. So our goal is to approximate what? F prime at the point x of y, right? So let's take this thing to the left hand side because that's our ultimate goal. So it had a what? 2h multiplied with it, right? So okay. So whatever we are going to have at the right hand side of this equation over here, it will have 2h multiplied with it, right? Fine. So what did we have? We had f of x sub I plus 1 at the left hand side. So we had this thing minus this term over here, which is the functional value at the point x sub I minus 1. Then we had these two terms, right? So since we have changed the side of these two terms, they will become what? Minus, right? So let's write it as minus, minus h cube by 3 factorial times f triple prime at the point C1 minus h cube by 3 factorial of the third derivative at the point C2. Okay, fine, very good. Okay, so that's what we have ended up with. Now let's try to simplify it further. Not technically simplify. Let's try to rewrite this equation a bit more clearly so that we can get a better idea of what the error complexity will be. Okay, so notice that we have h at the denominator and we have h at the numerator for two terms, right? So let's separate these two terms out so we can come up with h square, right? So h cube divided by h will be h square. So how do we write it? So let's isolate these two, the first two terms. We have f at the point x sub I plus 1 minus f at the point x sub I minus 1 divided by 2h. Then okay, and let's try to isolate these two terms. So this minus we're taking at the front. So we have what? We have okay, so let's skip one line and write it. So h cube by 3 factorial divided by 2h. What will it be? It will of course be what? H square by 3 factorial, right? So let's write it as something like this. Uh, h square by 3 factorial. Let's erase this term a bit. So we are going to isolate out this 2 as well. Okay, so h square, so h cube by h is h square, and this 3 factorial will come over here. And what we have remaining, we have f triple prime at the point C1. And since we have taken this minus outside, we have what plus over here, right? Because minus times plus is minus. So since we have factored out minus 1, so we have plus remaining over here. And since we have taken out h cube by 3 factorial term as well, we have what f triple prime, let me write it a bit more clearly, f triple prime at the point C2, right? And okay, so this 2h, the 2 of this 2h will come over here, right? So that's what we have remaining. So notice that what did we do over here? We have taken out the remainder term, the approximation of the remainder term, right? So this thing over here, if you recall, this was our formula for our central difference approximation, right? Which was what? The functional value of my point at the, the functional value at the point x sub I plus 1 minus the functional value at the point x sub I minus 1 divided by twice the step size, right? If you recall the formula. So this is our formula for our central difference method, central difference approximation method. And whatever else we have remaining is our error, right? The error that we are incurring, right? So you can see that the error has a factor of h square, right? So we can say what? We can say that whatever error that we will incur for this central difference method over here, when we adopt this central difference method, whatever error that we incur will be big O of h square, right? And again, another non-intuitive thing will be what? We are getting big O of h errors for forward and backward difference, but for central difference we're getting a greater complexity of error, right? So understand that here in practice conventionally we use very small values of h, okay? And we have, as you have seen from our last lecture, I think we have showed a graph, right? Looks something like this. So for values starting from 0 to 1, for those values we had what? We had h square values which were less than h values, right? So the values of h square starts to increase after surpassing the point 1, right? So this was our h square graph, h square function. This was our h function, right? So for very small, infinitesimally small values of h, we get a better error or a lesser error value for the central difference formula, okay? As opposed to the forward and the backward difference formula, where we get a larger error, okay, or a worse approximation. So of course a larger error translates to a worse approximation, right? And smaller error value just translates to a what? Better approximation, okay? So we can say that, okay, our central difference formula generally gives us a better approximation compared to our approximation that we get for our forward and backward difference formulas, okay? Fine. So now that we know how to analyze the error complexities, let's go back to our presentation and continue from there, okay? Okay, so these two are the error complexities that we have just tried to explain in our bamboo paper. You can go through the slide. The slide also explains the same thing. Okay, and we have talked about, up until now we have talked about the first derivative only. So for all higher order derivatives, the central difference formula still yields an error of big O of h square. Okay, so these are the formulas for the higher order derivatives. So you don't need to know their derivations. Okay, just try to understand how these formulas work. Just try to remember these formulas. Okay, so we'll talk about this in a bit. Okay, so we'll try to at least use this second order derivative in a bit. So before doing that, let's try to discuss about partial derivative approximation. Okay, so how do we approximate the derivatives of multivariate functions? Okay, so we know multivariate functions have more than one parameters, right? More than one parameter. And for multivariate functions we can calculate partial derivatives, right? So when we say if we have a multivariate for bivariate function, let's call it u, and it has two variables x and y, we can calculate the derivative with respect to y, and we can also calculate the derivative of u with respect to uh, sorry So we can calculate the derivative of u with respect to x, and we can also calculate the derivative of u with respect to y, right? So in order to come up with the approximation of these partial derivatives, we need to know the values of the bivariate function at some points, right? So if we arrange those discrete known points, the functional values at those discrete known points, we end up with a grid. Okay, so a 2D grid. Okay, so we say that okay, we know the functional values of the bivariate function at certain discrete grid points. Okay, so we'll of course arrange those grid points in a certain matrix. We'll see what the matrix looks like when we solve an example in a bit. Just hold your breath. Okay, fine. So we have u sub I. A conventional notation is that the functional value of my bivariate function at the point x sub I and y sub j. In short, we are going to denote it as y sub I comma j. Okay, so this is just a notational point that we are going to that I have just mentioned, so that you don't get confused for the rest of this lecture. Okay, fine. So okay, another thing that we're going to assume is that whatever discrete points that I have with me, the grid points that I have with me, they are evenly spaced. Okay, so for the 1D case, what did we see? They were evenly spaced by what? A magnitude of h, right? Our step size was h. Now for the 2D case, or for the bivariate case, the step size along the x direction will be h, and the step size along the y direction will be k. Okay, so after each h units, we are going to get a particular x value, and after each k units, we are going to get a particular y value. Okay, fine. So the central difference formula, so we are going to uh, uh, specifically talk about the central difference formula for the partial derivative approximation. Okay, since we have already seen that our forward difference formula and our backward difference formula gives us a worse approximation compared to our central difference formula. So we are not going to bother about the preceding two algorithms. Okay, our preceding two methods of approximating our derivative. We are just going to talk about our third approach, which is our central difference formula. Okay, so the partial derivative approximation, the central difference formula for that is something like this. Okay, so when we say u sub x of the point x sub I comma y sub j, we say that okay, the partial derivative of our bivariate function u with respect to x at the point x sub I and y sub j looks something like this. And if you look closely, it resembles what? It resembles the central difference formula for the for the x direction, right? So we have y sub I plus, sorry, u sub I plus 1 comma j minus u sub I minus 1 comma j, right? So this thing over here was our functional value at the I plus 1th point. This thing over here was what? Our functional value at the I minus 1th point, right? So since we are working with bivariate function right now, we are just going to change our x parameter, okay, or our x variable. Our y variable will remain constant, okay, and we're going to divide the whole thing by what? If you recall, we divided the whole thing by twice the step size, right? So since we know that the difference between consecutive x points was h, we know the difference between what? The x minus y point and the x plus I point, x sub I plus 1 point was what? 2h, right? So that's why we're going to use 2h as the denominator. Okay, so this is what the formula, the central difference formula for finding the partial derivative, or for approximating the partial derivative of a bivariate function u with respect to x at the point x sub I and y sub j looks like. Okay, and for the partial derivative of u with respect to y at the same point, it would look roughly similar, right? So instead of changing I, we are going to change j, right? So u sub I comma j plus 1 minus u sub I comma j minus 1. Okay, so j plus 1 and j minus 1. So these are the respective functional values at those particular points. So this is the functional value of the bivariate function at the point x sub I comma y sub j plus 1. This thing is the functional value of our bivariate function u at the point x sub I comma y sub j minus 1. Okay, so we are going to take that difference and we are going to divide it by twice of k. Why? Because our step size along the y direction, so this time we are approximating the partial derivative with respect to y, right? And we know along the y direction we had a step size of k, right? So we are going to divide it by twice of k because the distance between consecutive y values was k. So the distance between y sub I plus 1 and y sub I, uh, let's not call it I. So y sub j plus 1 and y sub j minus 1 is of course the difference, the distance between these 2 points is of course twice k, right? So that's why we are using twice k at the denominator. Okay, now the second partial derivative, second order partial derivatives, the formula would look something like this, roughly similar to the formula that we have seen over here. And if we calculate the second partial derivative with respect to x one time and with respect to y another time, so notice that it has x at the subscript, right? It means that the second partial derivative with respect to x, we are doing it twice. Okay, so this is the second partial derivative with respect to y. So it's essentially the same as writing what, let me change to a pen. So uxx, so ux, so, okay, let me go to the bamboo paper and write it more clearly there. Okay, let's switch back to the bamboo paper. Okay, let's go to the next page. Okay, so we say that our notation, so according to our notation, our u x at the point x sub I comma y sub j is the same as writing the partial derivative of u with respect to x, which will of course be delta with respect to x, what, at the point x sub I comma y sub j. Okay, so when we say the second partial derivative is denoted as something like this, u sub xx at the point x sub I comma y sub j. So of course this will be j is equal to what? The second derivative of the bivariate function u with respect to x at the point x sub I comma y sub j. Okay, so that this is the shortcut notation of this whole thing over here. Okay, fine. So we have seen the formula. Okay, let's go back to our presentation and see the formula. So these two are the formula of the second partial derivatives, okay, with respect to x and y respectively. Okay, fine. So roughly similar to this formula over here. So this thing over here is, let's go back to our bamboo paper and write it. Let's try to see the bigger notation of this thing over here. So we say that u sub xy at the point xi comma yj is the same as saying the partial derivative of something with respect to x. So this something over here will of course be what? The partial derivative of the bivariate function u with respect to y, right? So at first we are going to take the partial derivative of the bivariate function with respect to y, then we are going to again differentiate it, which means we are going to find the partial derivative of this whole thing over here with respect to x. Okay, this thing is the same as writing one. So this, since it's linear, we can of course get what, the partial derivative with respect to x at first. So the partial derivative of the bivariate function u with respect to x, let's do that at first, then we are going to partially differentiate with respect to y. Okay, so both of these are what, at the point x sub I comma y sub j, right? This thing is also same, x sub I comma y sub j. Okay, so this is what u sub xy at the point x sub I comma y sub j means. Okay, okay, so since we have just glossed over the formulas for these two, let's try to, for the sake of the completion, so for the sake of your understanding, let's try to derive the formula for this one. Okay, so let's try to do that. Okay, so we have seen that we are given what? We are given a set of discrete grid points, right? So let's try to let's try to draw what the grid points would roughly look like. So let's say these two are our axes. So this is of course, let's say, since we are going to denote it using a matrix, let's try to follow our matrix indexing pattern, which is something like what our uh, the, the rows are indexed using what I, and our columns are indexed using J, right? So let's say this is our x direction and this is our y direction. Okay, and let's say we have a particular point. Let's say this point over here. Let's say this point is the I comma jth point. Okay, or this is basically what? X sub I comma y sub j, right? This let's denote it using a short form, which is I comma j, right? So let's not write the brackets, otherwise it will become hectic. Okay, for me. Fine. So let's use a different color now. So this is our point I comma j, or x sub I comma y sub j. I'm writing it in short as I comma j, and our goal is to find out the derivative at this particular point. Okay. So for that, we're going to need its surrounding or neighboring 8 other points, right? So let's draw them. So this point over here, the point to its right, it will be what? It will be the I comma j plus 1th point, right? So we know in when we work with grids, the point at the right of a particular point will have its second index as plus 1, right? So if this index is j, this index will be j plus 1. The row index will remain the same, right? The column index will increase by 1, right? Okay, so let's use a different color. So now the point, let's say this is a pink point, which is what? At the left of my xi comma yj point. Let's say the index of this point is I, the column index, the row index will remain the same, the column index will decrease, right? J minus 1, right? Fine. So okay, now let's draw the points at the top of my intended point. So at the top we have what? So this thing over here, this blue colored point over here, will have the row index decremented by 1, right? So I minus 1, but the column index will remain as it is, which is j, right? Fine. And the point that's at the right hand side of this point, or diagonally to the top right of this point, or to the say the northeast of this intended point, it has what? It has the column index changed as well as the row index changed, right? So our column index will be our row index will be what? I plus 1, of course, right? I, sorry, not I plus 1, I minus 1, right? Because we are increasing along this direction, right? So I minus 1 comma, what will it be? It will be j plus 1, right? Because we're increasing j along this direction, right? J plus 1. Okay. And if we talk about this point over here, this is another one of its neighboring points, right? So this point is located at the northwest of my actual ij point, right? So in the index of this, the indices of this point will be what? I minus 1. The column index will decrease by 1, of course, and j minus 1, right? Fine. Now let's talk about the points below. Uh, let's use a different color over here. So let's say this thing over here is my what? Of course, I plus 1 comma j minus 1 point, right? And this thing over here is my what? I plus 1, and the j index will remain as it is. And finally, my last neighbor, which is somewhere over here, is I plus 1 comma j plus 1. This is of course the southeastern neighbor, right? Fine. So in order to calculate the or approximate the partial derivative of this particular point, we are going to need all these other points. Okay. So this thing is basically a what a bird's eye view of our bivariate function, right? So if you recall, bivariate functions look something like this, right? So we are going to need a 3D space in order to graph our bivariate function, right? So if we have say x along this direction and y along this direction, our bivariate functional value would look something like this, right? F of, or in order to maintain say consistency, let's write u of x comma y, right? So our bivariate function u will be along this axis, right? So normally we see our graphs look something like this, right? Our bivariate graphs look something like this. Say, right? This thing over here. So this surface over here is kind of all the functional values at some particular points of x and y. Okay, fine. So when say if you are looking, say if you are looking from this perspective over here. So this is a very bad drawing of an eye. So if we are looking from this point over here, we are going to see what? We are going to see something like this, right? We're going to see the given functional value at some given discrete points, right? So let's say this is our uh, x sub I, comma y sub j point over here. So of course, this is the functional value at this point. So if this is this point over here, the functional value or the value of u at that particular point will be over here, right? Of course. So this thing, this is of course x sub I, this is y sub j. Okay. So the value at this coordinate, the functional value of u at this coordinate will be what? Let me write it a bit more clearly. U of x sub I and y sub j. Okay. And okay, now since we are going to draw the derivative, right, at this point. So when we say try to find the ux, we say that okay, we're trying to find the derivative at this point with respect to x, right? It should look what something like this, right? And if we draw it with respect to y, say it looks something like this, right? Very very bad drawing, I understand. So let's say it looks something like this, right, along the y direction, roughly, right? Okay, so we call this thing our uy, and we call this thing our ux, right? This slope over here. Fine. So that was just to make you guys see what the grid points look like in actuality. But roughly, we are going to be given the matrix of the grid points. Okay. Fine. So our goal was what? So if I recall, our goal was to derive the uxy formula, right? So let's try to derive that just for the sake of your understanding. Uh, So we know that what our uxy at the point x sub I comma y sub j, our goal is to find out this formula, right? So we say that this thing has an approximate value of the, so of course we are going to, if you go back, we are going to have to use the central difference formula two times, right? So when we say we try to find the derivative, let's use a different color, the partial derivative, say not this color, of course, let's use a green color. Okay, so when we try to find ux is of course what we, when we find ux, we try to use what, u sub I plus 1, u sub I minus 1, and the j remains the same, right? So this thing over here, roughly this thing over here. So the green line has to pass through both of these 2 points, right? So this green line over here. So for consistency, let me use the same color. So this blue line over here that we have just drawn, we are going to draw it in this grid space over here. It would look roughly something like this, right? This will be my ux, because we utilize what, we utilize this point and this point in order to apply our central difference formula to approximate our ux, right? And for approximating our uy, which I have drawn using this purple colored line over here, this line should pass through both of these 2 points, right? So both of these 2 points, right? And we know that. Okay, so now that we know the basic things, let's try to see how we can derive the the partial derivative of u with respect to x one time, then again with respect to y. Okay, which means we're trying to find the second partial derivative with xy, right? Fine. So when we do that, we have seen that no matter along which direction we perform the partial differentiation, it doesn't matter, right? So let's say we perform the partial differentiation along the x-axis the first time. So what happens? So if we perform the partial differentiation along the x-axis the first time, we end up with what, u x. So not ux, sorry. So we have already performed the differentiation on the x-axis. So we are left with uy. So the derivative of u with respect to y at the point x sub I plus 1, comma, y sub j minus u of y at the point x sub I minus 1, y sub j. Okay, and at the denominator we have the twice of the step size, right? And we know, since we have performed the differentiation along the x-axis, our step size along the x-axis was h, right? So we are taking 2h. Fine. So let me change the color a bit. Okay, so now what do we do? We are going to expand these two terms. Okay, so let's see what they will look like. So instead of putting the equal sign first, let's try to expand them first. Okay, so what can we write instead of u sub y? We can apply the formula simply, right? So what do we get? We get u sub I plus 1. So I plus 1 will remain constant. And we have what, for j we are going to write j plus 1. So this is the functional value at the point x sub I plus 1 and y sub j plus 1. And then we're going to subtract what, u y plus 1 comma j minus 1, right? So this is the application of the central difference formula for this case only. Okay, so this thing will be what, divided by twice of k, right? So this time we are applying we are performing the differentiation across the y direction, right? Across the y axis, and we know the step size along the y direction is k, right? So we're going to put 2k at the denominator. Again, we are going to expand this term over here, which is something like say u sub I minus 1 will remain as it is because we're not working along the x direction anymore. I minus 1, and for j we are going to write j plus 1 and minus the functional value of u at the point I minus 1, which will remain as it is, and we have j minus 1, right? Fine. And just like before, we are going to use twice k at the denominator, okay, because our step size is k uh, along the y-axis, right? Along the y direction. And just like before, we are left with 2h at the denominator, right? So if we compile them together, what do we end up with? We end up with something like, so the equal sign, let's now put it. We end up with, so these 2h and these 2k terms, we can just multiply them and end up with 4 times h times k, right, as the denominator. And at the numerator, what do we have? If we expand it, we get what, u sub I plus 1 comma j plus 1 minus this term minus u sub I plus 1 comma j minus 1 minus this term over here u sub I minus 1 comma j plus 1, and this minus will become plus, right? So we have what we end up with, u sub I minus 1 comma j minus 1. Okay, so I think let's go back. This thing was the formula that we have seen back in our presentation, right? So let's verify it. So this thing was roughly the same as, let's go back to the presentation. Well, not roughly, it's exactly the same as the formula that we see over here. Okay, so that's how the second order formula gets derived. Okay, so the derivations are not important for your exams, just for the sake of your understanding and for the sake of closure, I've shown it in the paper. Okay, the derivations are pretty easy, right? Okay, fine. So now that we know how the second order derivations come, second order derivatives, the formula for the second order partial derivatives come. Let's try to solve an example that has been given in our lecture note. Let's try to solve that example using the formulas. Okay. So in the question you'll be given certain values at particular grid points. Okay, so at this grid points, the functional value of your bivariate function u at certain discrete points arranged in a grid shaped structure. Okay, and since we are given a grid, we can basically denote them with a matrix, right? So let's say you're given this matrix of functional values of u at certain points. Okay, so this thing will of course be our 1 comma 1 point, or the value, the index of I will be 1, the index of j will also be 1 for this point. We know how to say use indexing on matrix entries, right? So this is of course our 1 comma 1 entry. This is what 1 comma 2 entry, right? So our first index represents the column number. Our second index represents the row number, right? So this thing will have what 2 comma 2 indexing, right? Fine. So the question says that, okay, suppose that your step size along the x direction is 0.5 and your step size along the y direction is k, which is zero point 0.2. Okay, then it asks us to find the value of u sub y at the point x sub 2 comma y sub 4. So u sub y, if you recall, it's the same as finding the partial derivative of our bivariate function u with respect to y at this particular point. Okay, and since we already know what the formula is, we can just apply the formula. We can say that the partial derivative of at this point with respect to y is approximately equal to what u sub 2 comma 5. So we are using j plus 1 here, right? Our value of j is 4. So j plus 1 minus u sub I comma j minus 1, right? So j is 4, so 4 minus 1 is 3, divided by 2k because we are differentiating along the y direction, right? So with respect to y, right? So divided by 2k. If you plug these values into your calculator, so we know u sub 2 comma 5 is what? The second row, 1, 2, this is the second row, the fifth column, right? So 1, 2, 3, 4, 5 is the second row, fifth column entry of this given matrix. So you plug in 8.9 over here. So 2 comma 3 is what? 1, 2, 1, 2, 3. This is 7.8. You plug it in over here, and 2 times k is zero point 0.2, right? So you get 2.75. If you perform the calculation in a calculator, you should get 2.75. Okay, as your approximation of the partial derivative with respect to y at this particular point over here. So it's simple, right? You just look at the matrix, you plug in the respective values according to the formula that you're using, and you get the result, right? So of course we are using central difference for approximating the partial derivative, because we have seen beforehand that forward difference and backward difference doesn't give me really good approximations, right? The errors are very high, order of h, right? Fine. So now let's do a second partial derivative. So this time we'll use the final formula that we have just derived. So they are asking us to find the partial derivative of the bivariate function u, first with respect to x, then with respect to y at the same particular point. Okay, x sub 2 comma y sub 4. So this formula over here we're going to just apply it over here. So we know our value of I is 2 and our j is what? 4, right? So this is I plus 1, j plus 1. This thing over here is what? I plus 1, j minus 1. This thing over here is what? I minus 1, j plus 1. And this 1 comma 3 is what? Essentially I minus 1 and j minus 1, right? Exactly equal to this formula over here. And at the denominator we have 4 times h times k, because we had that over here as well. And just get the respective matrix entries. So 3 comma 5 is what? The third row, 1, 2, 3, third row, and the fifth column, right? 1, 2, 3, 4, 5. So this 9.1 over here, So 3 comma 3 is of course this one. 8 comma 8.4 is this one. 1 comma 5, right? So this one, and 7.5 is what? 1 comma 3, right? So first row, third column, this thing over here. Plug these values into your calculator and you're good to go. So h and k is what? zero point 0.5 and zero point 0.2 respectively. So after plugging these values into your calculator, you should get -2, right? So this thing will be your approximation of this second partial derivative with respect to x and y at the point x sub 2 comma y sub 4. Okay, so I think, yeah, that's it for this lecture. If you have any questions regarding anything, you can let me know. Okay, contact me through email, messenger, or WhatsApp, or you can also call me. Okay, so that's all from my side. Assalamu alaikum wa rahmatullahi wa barakatuh.